As with most mathematical functions that we do, these things are reversible. And so what we want to do is we want to, right now we've been going, hey, we have some variable. We turn it to a z-score, and then we turn it into a probability. And what we want to recognize is that this process is reversible. We can go from a probability to a z-score to our variable of interest. And so we have the ability to go backwards and forward. And so sometimes you might have a distribution, you might know something about it, its standard deviation and its mean, and you want to know how many things out of it you need to get a certain chance of something happening. And so that's why we would run down in this direction. And so what we do is we use our tables backwards. Is one way of doing it. We have, our technology has the ability to run these backwards, to do the inverse operation of our z-scores. And so we can kind of think in the process backwards. So for example, let's think in the process backwards. We have some data, something has happened, and we know it's normally distributed, and we know that our probability has the value of 0.3632. We know the area under the curve is 0.3632. And so what we want to be able to say is, what's that z-score? What's that z value related to whatever the mean is? Now, we haven't looked at any particular mean or any other part of the distribution, but what we're going to do is we're going to convert this into a z-score, and then from the z-score we're going to look at how we can move forward from there. So let's do this conversion. 2 seconds here. Need to get my table up. And so what we want to do is we want to find this value in the results of our table. So we come over here, and what we want to do, now this number, this percentage that came out is 30%. So we know it's less than 50%. And z-scores that were less than 50% are negative. And so what we need to do is we need to find the probability in the list of probabilities here. And so it was 0.3632. And so I look through here, and let's see where 0.3, so here's a 0.3632, it's right here. And that's at negative 0.35. And so this corresponds with a z-score of negative 0.35. We have the ability to take our data and come back. Well, we can have kind of a similar problem that we had before. We can have some distribution, and we know that the area to the right is 10.75%. And we want to figure out the z-score of this boundary. We want to know where this is and what things are 10.75%. And so what we actually do is we convert the percentage to the complement. We want to figure out how much stuff over here. We know everything's 100%. So 100 minus 10.75 is 89.25. Or in fractional forms, that's 0.8925. That's the probability of complement, or the probability of the stuff over here. And so we want to convert this to a z-score. And so what we're going to do is we're going to go back to our table, and we're going to look for this. Now, again, this number is greater than 50, so it's going to be in the positive z-scores. And so drawing the graph and knowing where our things go usually help us kind of figure out which table we're going to use or where we look at things. So if I come over here and I go to 0.8925, so somewhere here I have to find an 8925. I have to go through and find it 0.8925, 8962, 89, let's see, where are we here? 8.925 right here. So that's a 1.24. And so this corresponds to a z-score of 1.24. And so we're able to take percentages and turn them into a z-score. And this works for any percentage or percentile. And so any percentile is the area up to the number. Now, in our technology, the command we're going to use in Excel is that we're going to use the inverse. And so we could find the normal dot inverse of the percentage we want. And then we have 0 for our mean and 1 for our standard deviation. And what that does is we're working on something that we're calling the standard normal. And so what I want to do is I want to go through here and explain the standard normal coming across. And it's a thing we use now and these tables use, and it's the idea that when we've switched over to the z-score, we have a reference, and the reference that this table uses, or the standard normal uses, is that the mean is at 0 and the standard deviation is 1. And so when we look up these percentages from the values we're given, we map them over to the standard normal. And then we're going to take this standard normal z-scores that come out and map them back to our values. And so this standard score will work for anything that has a normal distribution. Anything that has a normal distribution, if we take these values in and out of these functions, we get a z-score. And the z-score says, hey, here's a standard normal. But our actual data we created our z-score from x minus mu over sigma, and we want to get back to x. And so a little algebraic manipulation, I multiply both sides by sigma, and then I add mu to both sides, and I have my equation for finding my x value. It's my random variable is going to be based off of the percentage I have. I find what z is, and I multiply it times sigma, and I add to it the mean. And so I can take this generic standard normal that's based off of the mean being 0 and the standard deviation being 1, and I can apply my actual data's standard deviation and my actual data's or distribution's mean, and I can get the boundary value. Right. Let's do one of these here using an inverse normal. I think I will go through, let's see, I think there's really only one example I want to use in the book. I'm either going to do the heavy, I'll do both examples, I think here. Let's do the cat one first. And so what we want to do is we want to talk about a cat at a veterinarian's. And then we'll do the police score. And so if you look at the veterinarian records of cats being weighed, the weights are normally distributed. So that means that there's some kind of true cat weight, and then in all the random growth and errors, push it around that mean. and the mean is 9 pounds. And the standard deviation is 2 pounds. And so if we found a cat and we said, hey, its weight was at 1.96 for a Z-score, well, we could go, well, what does that mean its weight is? Or if we asked for a percentage that gave 1.96. And so we go back to the idea that is how we convert from the variable. So this would be an animal at the top, roughly, I think, 95th percentile, maybe a little higher, but 1.96 is a common place on here. I think it's the 97th percentile. There's a given percentage for this. And so this cat is sitting up at the top of it. And we know the Z-score is 1.96. Well, what is that in weight we can talk about? And so, well, it had a Z-score of 1.96. I'm going to multiply that by 2 pounds. I'm going to add to that 9 pounds. And all said and done, that cat weighs 12.92 pounds. And so this is how we translate between our percentage via the Z-score and given our distribution's property, what its mean and standard deviation is, we get that boundary value. And let's see. Yeah. So I want to use the last example I'm going to do of percentages to Z-scores, and using the percentage to get an actual value will be the California Police Score one, like this one. So the idea is on a Peace Officer Standards training test, the test is set up that the mean score is 50 with a standard deviation of 10. What they're going to take is everyone in the top 10%. So that's what you have to take. You have to, this is what they're going to accept. And so if everyone does well, every shift. So there's a window that they can only take 10% of the people. They use the test as the metric, and the top 10% comes through. And so what we have to find is this boundary. What's the score that makes that boundary? Which in that case, if this is 10%, then everything up to it is 90%. And so we want the Z-score that relates to 90%. So we need to find the Z up to 90%. And so what we're looking for is 0.9. Now, what I'll do is I'm going to use the inverse normal function on the calculator, or on Excel. So that's norm dot inverse, and my percentage is 0.9, and my mean is 0. My standard deviation is 1. And that will spit out the value for me, the Z value for me. So let me come down here, make sure I'm typing this. Let me see if I can open up the window here to do this so we can see this. Trying to open this up. And let's see if we can get it here. I thought it was on this one. There it is. Alright, so I want to find norm inverse of 0.9 for a standard normal. and that gives me that the z-score is 1.2815, so on. Right, we see that z-score here, 1.2815. So let's see, I'm going to keep 4 decimal places, so 12816. The book might keep less, so I think the book only keeps 2 decimal places, so I'll do the same as the book for right now. And let me make sure I'm over here. So come over here. So the z-score is 1.28, keeping the same as the book. And so my x value is going to be the z-score times the standard deviation plus the mean, or 1.28 times 10 plus 50, which is what, 12.8 plus 50, 62.8. So you would need a 62.8 on the test to be part of the top 10%. Now I'm going to show you something that the calculator or the function in Excel has that makes this a little bit easier. And that is that, let me switch back over here. Now notice I've been using this thing called the standard normal, which I introduced talking here, is that we're saying that the mean is 0 and the standard deviation is 1. Well, I can get this to talk about my actual values for me. I use the norm inverse, and I want the 0.9, everything up to 0.9, but we said our mean was 50 and our standard deviation was 10. And there's my 62.81. And so the norm inverse function on Excel does the calculation for us. It tells us, what the probability space is before a particular value. Well, it can also find the particular value. And you want to be comfortable using both of these things. I think z-scores get talked about a lot. You'll hear z-scores being used when you use this stuff, but you want to be able to map, when you do this, what it means in your probability. Is 10% probability of being in this area. Well, what does that mean, 10% probability? And of course, the meaning versus calculation is something that we want to keep working on.